You should all get a warning that you're being recorded. I'm going to mute everyone. And I'm going to unmute Josh, I think. Actually, Josh, you might need to unmute yourself.
Okay, can you hear me? Okay. Yeah, all right.
Sri, do you want to unmute yourself and introduce Josh?
Sure. So, okay, welcome back everybody to this seminar. And the first speaker is Josh Pollitz from the University of Utah, who's going to speak about cohomological support varieties and their applications. And there was some confusion about the format, but just to be sure, Josh will present for the first 40 minutes, then there'll be a few minutes break, and then he'll continue until the end of the talk. Thank you. All yours, Josh.
Cool. Yeah. So thanks. Thanks to the organizers for inviting me to speak. It's really quite an honor to speak in this seminar. And thank you everyone for showing up today. Also anyone that watches the video later, really appreciate it. So I'm going to talk about these cohomological support varieties that I've been interested in the past several years. And just to give you an outline of the talk and where we're going. So I first want to motivate them. I don't think we've had a talk in this seminar that has dealt with support varieties and commutative algebra. I think we saw a few non-commutative settings, some nice talks of Yulia Petsova and Chris Negron. So I'll start with motivation, and then I'll tell you what they are, give you the definition, but then lots of examples of these support varieties. And then I'll discuss some structural applications, and I'll say more when we get to that part of the talk. And that's kind of the first, the first chunk. So hopefully, if I time this out right, roughly the first 40 minutes or so. And then the last part, the second part of the talk, I want to talk about, is it something weird going on? Sorry, it's like, oh, never mind. Sorry, it's my screen. Okay, I see what's happening. Sorry. Okay, anyways. Okay. Yeah, so in the last part of the talk, I want to talk about upcoming joint work with, so this is with Ben Briggs and Eloisa Griffo, where we have kind of established some new insights about these varieties, and then also have some kind of interesting applications of them. So I want to talk about that in the second part. Okay, so let's start with the motivation. All right, so throughout, let's fix a commutative Noetherian ring R. And I'll assume it's local. And let's let K be the residue field. Sorry, and I don't really need to do this, but maybe just to play it safe for today, I'll assume K is algebraically closed. And okay, so the story starts, I guess, in 1989, at least in local algebra. So in 89, Lucho Avramov introduced an assignment sorry, my hand's a bit shaky right now. Okay, so what does it do? It takes a finitely generated R module and it assigns to it some cone, some Zariski closed conical subset. So you could also think of it as the projective variety, if you like. So, so some closed cone in affine n space. Okay, and I'll tell you what this number, what this n is in a second. So it takes some module m and it assigns it to what I'll denote as VR of m. And so this is what the cohomological support variety is. Ah, geez. Okay, and so what is this n? This n is the number, it's the number of relations that define R. So the number of relations Oh, jeez. Oh, I'm sorry, guys. Oh, sorry, all. It's awfully shaky right now. So what do I mean? I just mean that if you have a regular, sorry, if you try to express your ring as a regular ring modulo some ideal, it's just the number of generators for that ideal, number of minimal generators for that ideal. Okay, if I stopped here, I mean, this assignment may not be interesting, right? Could do anything, but the point is it actually reflects interesting information about the module. So where VR of M encodes interesting homological information. Ooh. About M, sorry. And later I'll actually talk about how this assignment actually can tell you some interesting homological information about R itself as well. Okay, so if I'm telling the story, I guess historically though, when Lucio was looking at these varieties in the context of complete intersection rings. So for now, let's let R be complete intersection. And this will come up, several times. We'll focus on CI rings. So, and just to get the, the definition down, so if you take your ring and you write it as a regular ring, modulo some ideal, or you complete it and do this. So you have some regular ring, modulo some ideal. What I want is I want Q to be, so Q is regular. And the F's form a Q regular sequence. Okay. So the application, so to motivate these varieties, the application is going to be in this setting for complete intersection rings. And here's what I think is, I don't know, this is one of the more beautiful applications of this theory. Kind of got me interested in this. So this is due to Avramov and Bookvites in 2000. Okay. So what does it say? It says, if R is a complete intersection ring, so if R is CI, and you take two finitely generated R modules, then there's symmetry in the cohomology modules for defining, or there's symmetry in X modules for M and N. So then complexity of MN is the complexity of N against M. And so I'll give you the definition of this and then try to explain what's going on here, of this invariant at least. So complexity, what it is it's an asymptotic measure of the minimal number of generators of X modules. So this is X of M against N. So what it is the infimum for all non-negative integers, such that there exists some A where when you look at, I guess, the K vector space rank of X R I M N tensor K. Okay, so this value right here is just the minimal number of generators of X I M against N. What you want is you want this to be less than or equal to A I B minus 1 for all I sufficiently large. Okay, so what this is supposed to be telling you is kind of how fast this sequence of numbers, the minimal number of generators of Xi, is growing polynomially. And just for an example, so if you think about complexity 0 and you stare at the definition, complexity 0 is equivalent to X vanishing. And complexity 1, sorry, X eventually vanishing. Complexity 1 is saying that the the minimal number of generators of these X modules are eventually bounded, and then complexity 2 says they can grow at most linearly, and so on. So it's some polynomial measure of growth. I find this, it's quite of a shocking theorem at first when you think about X. I mean, it's highly non-symmetric, right? Xm against n and xn against m are drastically kind of different things, but yet over a CI ring, I mean, there's this kind of remarkable symmetry in these X modules. This is something that certainly does not hold over non-complete intersection rings, kind of fail quite badly. Okay, and just to mention some consequences. So one is that if you think about the X vanishing of m against n, this is actually equivalent to, over a CI ring, the X vanishing of n against m, eventual vanishing. Okay. And another one is that, oops, 1 and B, okay, sorry, 2, is that if you think of the sequence of Betty numbers, well, if I think about this sequence of Betty numbers, that's kind of like studying complexity of m against k, right? Because you'd be looking at x k here, and then you would just honestly have your Betty numbers, right? And if instead you look at complexity k here and k here, those are your Bass numbers. And so this actually tells you that minimal free resolutions and kind of minimal injective resolutions grow at the same rate, polynomial rate over CIs. So the Betty numbers and Bass numbers grow at the same polynomial rate. Okay, and in the sense they have the same complexity, there's actually recent work of Ben Briggs, Daniel McCormick, and I, and also you can recover this with work of Eisenbud, Pave, and Schreier, that you can make a more precise statement in which that they actually asymptotically are almost the same. So just kind of leave it as a vague statement there. Okay, so that's motivation, but I certainly owe you a definition and lots of examples of maybe what these things are. So that's the next part of the talk. Okay, so part 2. So definition and examples. And so the definition is it's a little complicated. It just takes a tiny bit of setup. So I'm going to try to do that now. So let's write the completion as a regular ring modulo some ideal. So with Q regular. And let's say I is minimally generated by n elements, F1 up to Fn. And let's do this in a minimal way. So we take a minimal Cohen presentation. All right. And so where these varieties live is they live in the space of minimal generators for this ideal I. So they live in the space of relations defining R. So what I want to do is introduce the space of relations. Defining R. And that's the affine space in which these varieties are going to live. So the affine space over n, over k, where k is the residue field. So just k to the n. So I'm just thinking of n tuples, and I'm thinking of this bijectively with I mod mi. So the space of minimal generators for I. Right, and so through this correspondence, if I have some tuple A1 up to AN, this is corresponding to the minimal generator. I'll denote as FA. So it's the image of that minimal generator in this quotient. And this is just the sum of FIs. Hey guys. Okay, so so basically I'm just fixing as my basis the images of the, this minimal generating set. I'm fixing their images as the basis for this vector space, this K vector space. Okay, and so the idea behind defining these varieties is what we want to do is approximate homological properties of R by using intermediate hypersurfaces. I'll say a word about that in a second. So, okay, so the idea is to approximate homological properties over R using intermediate hypersurfaces. Where I'm thinking of these intermediate hypersurfaces as being parameterized by this affine end space. So you kind of have you have these parameters. Okay, so so if I take some point in affine end space, a non-zero point here, this corresponds to some f sub a, so some minimal generator for I. And it's a non-unique correspondence, right? I mean, there's a choice here. You've picked a point in this affine space, and you take the image, of some minimal generator. And now I've picked some minimal generator. And what we want to do is, so we take. So you have the usual surjection from Q to R hat, I guess from above in the setup. And what we want to do is factor it through this intermediate hypersurface ring. Okay, and so let me just a comment here is this thing is a singular. This is a singular hypersurface. Ring. And what we're interested in doing is studying, let's say you have some R module. So you have, oops. So you have R acting on some module M, and you can go along this faithfully flat extension to M hat. And so what you're interested in doing is studying homological properties, of M over R, and you might pass to the completion along this faithfully flat map and try to study the properties of M hat over R hat and see what you can say, maybe things like Betty numbers or growth of Betty numbers and whatnot. And sorry, I lost my train of thought. And I guess the point is homological algebra of, over just arbitrary rings can be quite complicated, right? I mean, we don't expect very nice properties in general. But if I'm interested in maybe asymptotic information, if I restrict back all the way to Q, which is a regular ring, you kind of lost all the asymptotic information. So that's kind of too far to restrict back. But if you kind of just go one step, and you could go to these intermediate hypersurfaces, there's still a lot of interesting, rich information here. So like, for example, and they're relatively well understood, the homological algebra over these hypersurface rings. So for example, thanks to David Eisenberg's theory of matrix factorizations, we know, as a button 80, we know that all minimal free resolutions over such rings are eventually two periodic and so on. So minimal resolutions are eventually two periodic and given by a matrix factorization. So kind of when you work over these hypersurface rings, you have access to kind of more computational tools if you're trying to understand the asymptotic properties. And now the idea is to not just study it over one intermediate hypersurface, but study it over all of these intermediate hypersurfaces. So you kind of let A vary, so you picked a point A, but now if you let A vary among all points in affine space and you try to glue together the data, maybe you can learn something about the original properties of M over R. So that's the idea behind the definition. So now let me give you the definition though. And then, like I said, I'll do examples for sure. All right, so the definition. Okay, so the cohomological support variety of M and maybe I'll assume it's non-zero, is, well, so I'll denote it like we did before. So it's VR of M. So it's the set of points in the affine space where the asymptotic properties of M don't vanish. So you're trying to pay attention to the points where there's still interesting information to study about M. So that can be captured by saying when you look at the intermediate hypersurface, Q mod FA, you want this to have infinite projective dimension. Okay, I guess when you make this definition, it's kind of a theorem that this is well defined, right? So you're picking a point in affine space, and then you're saying that you want the projected dimension to be infinite. Well, you need to know that that's independent of the choice of lift, the choice of minimal generator that you picked. And so that ends up being true, but actually more is true. Even the Betty numbers or Bass numbers are still the same, and so on, like over those intermediate hypersurfaces. Okay, so that's the definition. A quick fact. I guess due to Avramov, when the ring is CI, and then Jorgensen and several others, so Dave Jorgensen, several others more generally, is that this thing is always a closed, so BR of M is a closed conical subset of affine end space. I guess when M is finally generated. Okay, and the fact that it's a cone isn't so hard to see. That just means, if I started with some point in the variety, if I scaled it by any constant, anything in K, it's still in the variety. And the point is that if you scale this minimal generator by any point and then you look at this hypersurface, you actually haven't changed the ring at all, right? So it doesn't change that. So that the conical part is less of a proposition, or that's just kind of built into the definition. The fact it's closed is something to work out. And I'll just want to mention a convention here that if I look at the variety of 0, at least for today, I'll just define it to be empty. This kind of works better if you're working more scheme theoretically as well. So, okay, that's the definition. I know it took a little bit to get here, but I want to do lots of examples now to tell you what these things are. That's the plan. Okay, so first one, I look at VR of K, the residue field itself. So this ends up being all of affine end space, as always. And this isn't hard to see. The point is if you took some non-zero point, then what we already said is that each of these Q mod FAs, these are singular. So it's not regular. And so the projective dimension is infinite at all of these points. Great. Okay, so that's kind of easy to see. And I just want to pause for a second and make a comment here. When you think of the usual support, so the spec R support, okay, well, this is kind of as small as possible, right? It's just the maximal ideal. But when you compare that to the cohomological support, you're getting all of affine end space. And so this is supposed to reflect the fact that K is, it's an extremal R module. So it has, its resolution has extremal properties. It grows kind of as fast as possible. Okay, and it's, an interesting test object to study homologically. Okay, so that's one example, maybe one more concrete one, or not one more concrete one, but let's do a concrete one. Let's say I look at R being this ring, and let's say M is R mod X minus Y. Okay, and so we could ask, well, what is the variety of M? So just to make it clear, in this example, there's 2 generators for my ideal. So this will live in affine 2 space. We want to know what this variety is. Okay, and so you can maybe I just want to make the point that these things in specific settings are very computable with things like Macaulay too. So a direct calculation shows the minimal free resolution free res of M over maybe QA, so this will be Q mod FA with A non-zero, has the form. Okay, so there's two cases. Sorry. It's not going back. Okay, there it is. Sorry. Okay, so QA 0. So this is X minus Y. So this is when A1 is not equal to negative A2. And when A1 equals negative A2, you can show that the resolution is a very particular form. So it's QA2, 2, and so on. And you can write down these matrices explicitly. So for example, this is X minus Y, Y squared. This one is, sorry, X plus Y, 0, negative Y squared, X minus Y, and then X plus Y, sorry, X minus Y. Zero, Y squared, X plus Y. And then it just repeats from there on. So and it's a concrete calculation that you can calculate the matrices that appear. And so from this, you can see that what's the support variety of M in this example? It's the off diagonal, right? So it's A1, so it's negative A2. Oops. Okay, so it's, all right. So there's a concrete calculation, but this example is actually part of a kind of a more general example. So more generally, if you have a map, a surjective map to Q mod J, where this is CI, then you can always calculate the support variety of Q mod J over R. And so it's the following. So then, and it's given in terms of, it's kind of, so it's given in terms of the following. So remember, R hat was Q mod I. And so if you look at this, this was our affine end space, so I mod MI, you get this induced map onto to Q, sorry, it's a J mod MJ. If you take the kernel of this map of vector spaces, this is actually the support variety of Q mod J. So this is kind of a more general thing. And this is, I guess, calculated by myself and Ben Briggs and Eloisa Griffo. But that's, I mean, so this example above fits into that setting. Okay, so there's this example. I want to do more though. So 4, let's say R is CI. So if R itself is CI, then there's a very well understood of what kind of happens for when a cohomological support variety can be as small as possible. So when it can be a trivial cone, I guess this is if and only if M has finite projective dimension. I guess by my conventions, maybe it's non-zero. So but what I want to pull away from this is that if you look at the variety of R itself, particularly if you look at VR of R, and that's always just 0, just the origin. Okay. So you could look at this and ask, well, what happens if R is not CI? Can you say anything about all these varieties? And that's kind of took some work. So 2019, I guess the following are equivalent. So it's that R is CI. That's equivalent to the variety of the ring itself being the origin, so being small. And that's also equivalent to the variety of M being the origin for some finite generated R module M. And really the interesting thing here is kind of the either B implies A or C implies A, right? So the right, we already know that we kind of know the story for CIs that's given by part 4, but yeah, so the interesting thing is kind of, you know, B implies A or C implies A. And this has kind of motivated a lot of things that I've looked into, but then also the work with Ben and Eloisa that I'm going to mention later is this makes this object in particular, not this one, but I'll just say it, this makes VR of R kind of an interesting invariant, geometric invariant. Interesting geometric invariant to study when R is not complete intersection. And maybe some examples in that direction. And that is part of the theme of what I'll talk about later. So I'll come back to that idea. So maybe some examples that witness this. So let's say R is K, X, Y, Z, and X, Y, Z. If I look at VR of R, okay, so, you know, where does this thing even live? Well, there's 2 generators, so it lives in affine 2 space, and it turns out that this is the whole space. So I mean, this is kind of saying, you know, well, that this is kind of failing. Well, this theorem above is kind of failing in the worst way possible. The variety is actually as large as possible for this ring, and this is an example of what's called a Golod ring. And actually, for all Golod rings, you'll have this behavior where their variety is as large as possible. Maybe come back to this also later. Maybe one more example. Okay, so the following, let's say R is K, X, Y, W. And then you kind of twist the variables. So you do X squared, XY, YZ, ZW, W squared. And you might ask, what's VR of R? So in this example, well, you count them out. So there's, I guess, 5 generators, right? So this is going to live in affine 5 space. And it lives in here. And it's not equal. In this example, it's a union of hyperplanes. So it ends up being the X or the A1 equals 0 hyperplane, and the A5 equals 0 hyperplane, the union of them. But in general, I mean, it's not really quite a clear picture yet for what types of ring theoretic properties directly translate to VR of R. But that's kind of an interesting avenue that I'd like to talk more about. Okay, so maybe before I switch gears and talk about some applications, maybe this is a good place to just ask if there are any questions. Okay. So before I take a break, oh, sorry.
Can I ask something, Josh?
Oh, yeah, sorry.
Yeah, so I was just wondering, like, probably the behavior over the direct sums is also probably studied, right? Like M direct sum M.
Yeah, so that ends up being the union of the
Yeah,
the 2
that would make sense. Absolutely. All right.
No, exactly. So there's lots of nice yeah, things you can say, but
yeah, absolutely. Sorry. Yeah.
Oh, no. Okay. So should I take a break at 45? Does that sound about the right time?
Sounds good. If you think this is a good place to take a break.
No,
go ahead.
I'd like to,
Okay.
yeah, I'd like to at least do a tiny bit more, and then I'll take a break.
Yeah, then do that. Yeah.
Okay, so I want to just mention some structural applications. Okay, and so I guess these structural applications are going to be phrased in terms of the derived category of R. It's not really going to be important for the the stuff at the end of the talk with Ben and Elisa. So if you don't follow this part, don't worry. I mean, there'll be some interesting stuff that happens later as well. But I want to mention this because it shows how studying these varieties can be, it's kind of a powerful theory that can prove interesting things. So that's what I want to mention next is, so let's let dr be the derived category of R. And so I just mean take all complexes of R modules and formally invert the quasi-isomorphisms. Okay, and you don't really need to know a ton about this gadget, but this is a triangulated category. And so, in particular, there's a notion of suspension. There's, and here it's just shifting a complex. And then there's also, exact triangles. And at least if you aren't familiar with this, you can just think of kind of short exact sequences of complexes. And whatnot. But what I want to do is leverage the triangulated structure to get applications in local algebra. Okay, so that's what's going to happen next. And so the setting in which this happens, so it's in a slightly smaller category. So just how when you're studying all modules, or modules, we kind of sometimes restrict to the category of finitely generated ones. Well, inside the derived category, there's an analog of that, the bounded derived category, finally generated R modules. So I'll call that df of R. So it's supposed to be analogous to studying finitely generated modules. And so this contains all complexes M with, when you look at its homology, it's finitely generated. Okay. So one thing I want to maybe comment about this category is that DFR is a thick subcategory. It's a thick subcategory, and so I just mean that it's also a triangulated subcategory of DFR. So it's a triangulated subcategory of the derived category. So it's closed under shifts and triangles or forming mapping cones. And it's also closed under taking direct summons. Okay. So more generally, if I have an object M, so some complex of R modules, it's interesting to look at the smallest thick subcategory of M. So I'll denote that with bracket. So this is the smallest thick subcategory of D of R containing M. And kind of, well, I guess the idea is, if you have some object that's in this category, if you have nice homological properties of M, they usually descend to nice homological properties of that object that's also in that category. So it's a kind of natural thing to study. Just a quick example is if I look at the thick subcategory generated by R itself, this ends up being the category of perfect complexes. So the things that all complexes M that are quasi-isomorphic to some bounded complex of finitely generated projectives. Okay. So what I want to do just quickly is rephrase one of the most celebrated theorems using homological methods in commutative algebra. So the Auslander-Buchsbaum-Serre theorem. I want to just rephrase it in this setting. So regularity of the ring, so R is regular, if and only if DFR, so everything in the bounded derived category, DFR, is also in the smallest thick subcategory generated by R. Right, and so this side over here is saying that everything has finite projective dimension. right? Every complex is finite projective dimension. Every module is finite projective dimension. And I bring this up, I mean, I think people here probably all know, I mean, one of the reasons this is such a beautiful theorem is it solves the localization problem for regular rings. And you could ask, is there an analog of this theorem, this kind of structural theorem for complete intersection rings for CIs, right? So what is there an analog for CIs? And building off the work of Dwyer, Greenlease, Iyengar in the early 2000s, I answered a question of theirs using this support theory. So that's what I'd like to mention. So 2019 is that there's an analog. So it's R's CI if and only if. So I'll write it and then I'll maybe try to reinterpret the Auslander-Book-Spon-Steyer theorem above. So if you take something in the bounded derived category, maybe non-zero, then if I look at how the smallest thick subcategory containing M and the smallest thick subcategory containing R intersect, I don't want this to be zero. Okay. And just to quickly reinterpret, I guess, the theorem above, you could say that if you have some M, what you're asking is that M intersect R is actually giving you back M. Okay, in terms of this thick subcategory business. So you can see this is some weakening of it. And I should say, I guess, so Dwyer, Greenlease, and Iyengar, so DGI, they proved the forward direction. I mean, there's kind of several different ways to prove it. It's not the hard direction. They asked about the reverse direction. And maybe for time's sake, I was going to maybe mention how these varieties were used, but I don't think I'm really going to be able to say much because I want to get to the other stuff. So maybe I'll just point out is that these support, VR of R in particular plays a big role. In establishing this. Maybe if people are interested, I can say more later, but I don't want to dwell on this point. Maybe I think for time's sake, maybe this is a good place to stop. Maybe.
Okay, thanks, Josh. How about a 5-minute break? We can start at 50 past the hour. It's 45 past the hour now. But if you have questions, you're welcome to ask them now, unless Josh also wants a break.
No, I'm good.
I'll be back.
May I ask a question, Josh?
Oh, yep.
Yeah. So, can you tell me can you generalize the? I mean, can you go to the first page, like where you were defining the cone, the cohomological support?
Like the definition?
Yeah. Little later where you were defining. Yes. Here. So can you generalize? So I have actually two kind of questions. So first is, can you generalize this definition when your ring is not local?
I mean, do you want like a graded ring? I mean, I guess like you need some notion of like minimal, like a well-defined space of minimal relations, right? I mean, this definition, I mean, if you're like you take a graded ring, maybe, right? And you can look at this this kind of analogous thing there. I mean, actually, to answer your question, I mean, these varieties that I'm talking about right now, I've defined them living in affine space over K. They kind of naturally actually live in affine space over R, or there's an extension of them, I would say, that lives there. And those varieties, you don't really, you still need.
So actually, I don't know any of these kind of things, but I was trying to understand the notion and its relation with actually support of a module. So they're not same. Like, can you literally relate it with something support where you are localizing and it is not zero in that way?
But I think this example kind of shows that it's kind of drastically different than the support of, is it I
Mhm.
mean, because this is like, the support of K is just the maximal ideal, whereas I don't know. I mean,
I see. I see.
this would kind of, indicate that it's a much different kind of geometry than geometry, right? So that's why it's maybe nice to say cohomological support, because it's like some type of cohomological information. If anyone else has thoughts.
Okay, I'm gonna pause the recording for a minute until we restart again.
That one, number 6. Number
Oh.
6. So that was getting me to, or 6 and 7 were both getting me to think. Have you guys found any computations on certain types of singularities? So if you had, say, I'm thinking characteristic P, if you have an F pure singularity or an F regular singularity, what the VR of R should be?
I don't think we've thought about that. That's an interesting question. I mean, we've looked at kind of other like kind of homological-ish rings, like Golod rings. We can say exactly what happens, and yeah, I mean, we haven't examined kind of how the F singularities might determine the variety, though. I don't think.
Okay.
Like
Okay,
this.
thanks.
Maybe for that, you would rather look at the support or the variety associated with these Frobenius push forwards of the ring. That might be interesting.
Hmm.
I mean, we know something for high push forwards, but not in general, right?
Oh no, wouldn't the supports be like always full?
Yeah,
or,
eventually.
Okay. Yeah. Okay. Oh, I see what you're saying.
Okay, maybe you can, it's about time. You want to pick up again, Josh?
Okay. All right. So, yeah, I was going to mention a bit more. Maybe I'll just say in just in words. So, yeah. So, actually, no. Sorry, I never got to finish my thought here. So, there's this theorem here that I was mentioning, and then really the upshot of this that I just totally forgot to mention is, the reason you might want to prove a result like this is the thing on the right-hand side here, this condition actually localizes, just how, in the Oscillander Book's-Baum Sayre theorem, when you localize this, you get the quality remaining. So the point really here is that you characterize the CI property in terms of something that localizes well. And so as a consequence, you get a new kind of structural proof of the theorem of Lucho Avramov, is that if R is CI, then R localized at P is CI. Right, for any prime. Okay, and so just trying to make the point that there are interesting ring theoretic applications of these supports, and maybe I'll just say the name I was going to mention. Another result of so Greg Stevenson that actually says that over complete intersection rings, these varieties tell you a lot about how things are related in the derived category. But maybe for time's sake, let's go ahead and move on to the upcoming work. Okay, so right, upcoming work. So this is with joint with Ben Briggs and Louisa Griffo. And so, I mean, here's the problem is, okay, so we have this, so yeah, so support varieties, they naturally extend to defining them on complexes. So we define them for modules, but there's a way to define it for any complex. Find n space, so it takes some complex, it gives you some cone, and so there's this assignment. So So any complex, you can associate to it its cohomological support variety. And there's a question, so something called the realizability question. Which asks, is this surjective? So kind of what types of cohomological support varieties can you get? Right? Are there any types of restrictions, maybe based on ring theoretic properties? So that is, it's every closed cone in affine n space of the form VR of M for some complex with finitely generated homology. So, I mean, if you just restrict it to modules, kind of my earlier work already said that's not the case, right? And so, this support theory really is kind of interesting on the whole derived category. So this is kind of the natural question to ask. And it turns out that this is a rather hard question to answer in general. Like, we don't really have a good understanding of what supports you can realize when you get the supports of complexes. But there are some positive results. So theorem of Peter-Berg, Avramov, and Iyengar, and also Jesse Burke and Mark Walker. Says that if R is CI, then it is surjective. So every closed cone in affine n space is actually the support variety of some. In that case, you can say it's the support variety of some module. So. Okay. But if R is not CI, I mean, there really hasn't been much. So what I want to tell you about is this theorem with Ben and Alyssa. It's better in kind of understanding what types of supports you can realize. So it's theorem 1. Work that will appear soon. So if you take a complex, there's always, so I guess maybe I should have sold this. So I guess answering this question is kind of hard. You kind of, if you look at this assignment and you're trying to figure out which cones you can actually get, I mean, that's a very hard question. So what we did in this project is we tried to look for just bounds on the dimension of these varieties instead. And if we could cook up bounds on the dimension, maybe we could answer this question. And then it turns out that we could actually not only answer this question, but establish some interesting connections between some different parts of local algebra that have some pretty cool applications. So okay, so here's the bound we figured out. So the dimension of the variety is always at least n minus the codepth. Oh, sorry, n minus the depth. Wow, I'm getting this all backwards. Sorry, let me just slow down. So n minus the embedding dimension of R. So the minimal number of generators for the maximal ideal plus the depth. So what I was about to write was the codepth, n minus the codepth. Okay, and actually this is strict with strict inequality. When R is not CI. And so a nice consequence of this is that in particular, if R is Cohen-Macaulay and not CI, then that actually tells you that the dimension of these varieties is always at least 2. And so not only does the realizability question fail for Cohen-Macaulay non-CIs, I mean, you can't get any lines either, any lines through the origin. And maybe it's worth saying, at least in examples, it does seem like the bound should be much bigger than this in general. So suggests probably stronger bounds. But this is kind of a first step and a first insight that you can actually bound the dimension away from 2. And so maybe just to maybe make that clear, just in case it's not. So quick remark. So if R is Co-Macaulay, then when I look at n minus the embedding dimension of R plus the depth of R, and I remember that R hat was Q mod I, you can write this as the minimum, so this is n minus the height of I, which is always not negative, and this is a quality exactly when R is CI. When I is generated by a regular sequence, right? And so actually, so if you have a non-CI, I feel like I have a bound off here. Oh yeah, no, sorry. So yeah, so actually, here it comes. So when you have a non-CI, part of the theorem says that this inequality becomes strict, and then so does this one. So that's how we get the 2. Okay, so that's the first theorem, but there's still, I'll mention a little bit about what goes into the proof in a second, but I just want to at least just make a comment that what we still don't know, which I think would be interesting to settle, is, so if R is not CI, and M is in DFR, non-zero, does, well, I guess we can just say, can VR of M be the origin? Or even just more generally, what's the smallest variety that's realizable? What's the smallest dimension of a variety that is realizable? So I guess we now know this for Cohn-Macaulay rings, right? Cohn-Macaulay non-CI rings, but we don't know. We have possible ideas. I would kind of guess that if you don't have a CI, you certainly can't get the origin. And in examples, it does seem like these varieties are quite big. So I view these varieties as some type of geometric obstruction to complete intersections. Right? So one place that we do know where you can say something is for Golod rings. And in fact, we know the whole story there. We know exactly the varieties that are realizable. So as far as Golod, then VR of M, it can only be 3 things. So it's either the empty set, all of affine, n space, or a hyperplane. And all of them are realizable. Right, okay. So that's a situation. So I guess in some sense, for CIs, we know exactly what happens. You can realize every single variety. And for Golod rings, there's 3 options. It's either your the support variety of 0, or the support variety of K, or you're some kind of hyperplane. Okay. So this is theorem 1. And I want to mention a second theorem that is kind of in a different direction. So it's going to take a tiny bit of setup.
So Josh, if M is non-zero, it's just the full thing or a hyperplane, right? That's the content?
Yeah, that's the content. And so it's very, right. And so actually from like a thick subcategory perspective, this actually puts lots of restrictions on thick subcategories and so on. So there's a lot of interesting things going on here. It's saying that Golod, yeah, exactly. Golod rings, there's only kind of 2 types of modules, at least as far as support can see. Okay. Okay, so I want to go in a slightly different direction in this work with Ben and Eloisa. So let's say R is local, as it's been, sorry, but let's just fix some notation, and M is an R module. then just to remind you, the Lowy length of M is the following. So it's the least non-negative integer such that the maximal ideal annihilates your module. Okay, and some quick examples. If you have Lowy length 1, well, that says the maximal ideal annihilates the modules. That's if M is a K-space. Maybe a more concrete example. Maybe. So I look at K adjoint XY, go mod X cubed and Y cubed, and I look at the Lowy length of R itself. So if I want to imagine what the ring looks like, I've killed all the monomials that are divisible by degree or by X cubed. And on the other side, I have Y squared, Y cubed, killed everything here. And so I have just the remaining elements in here. And now I can think of my ring being filtered by the various powers of the maximal ideal. And so I don't know if this picture is helpful, but you can then read off from here the Lowy length, X2 is 5, right? Everything past degree 5 is 0. Okay. Whereas, this is, so this invariant, maybe I'm just trying to make the point, this invariant's much different than length, right? If I wanted to calculate the length, I'm just going and counting up these lattice points. Right? So, okay, so let me state, or this is kind of a not really precise mathematics. And then I want to state a theorem. So the motto is that if R admits a module, a non-zero module, with small Lowy length, and finite projective dimension, then R should be suitably nice. The singularity of R shouldn't be that bad. For example, if the Lowy length of M is 1 and M has finite projective dimension, I mean, that implies you have a regular ring. Okay, and so I want to state a theorem that kind of makes this a bit more precise and builds on some bounds that were established in homotopy theory. And it's the following theorem. So due to Avramov, Bookbites, Iyengar, and Claudia Miller in 2010. So it says is the following. So let's say you have some finite free R complex. So imagine maybe a finite free resolution of a R module. And let's assume that it's non-zero homology, it's not contractible. Then there is a bound on the Lowy length of the homology modules. And it's at least the conormal free ring. Of R plus 1. Okay, and so this is where conormal free ring of R. So what is it? It's kind of what it sounds like. It's so you take the conormal module of R and you try to find the maximal free direct summon in there. So it's that rank of the maximal free direct summon. So it's the soup over M such that when you look at I mod I squared, there's a free summon of rank M that splits off for the conormal module. And this is where you range over all minimal Cohen presentations. Okay, so for example, if R is a complete intersection ring, so if R is CI, then the conormal free rank is just the codimension, what I've been calling N throughout. And so that actually tells you that there's a a priori bound on this. It's at least N plus 1. This is the codimension of R. Okay. All right, so the second theorem I want to tell you about with Ben and Elisa is the following theorem, so theorem 2. So it recovers this theorem and gives us a stronger bound in various cases. So Briggs, Griffo, myself, okay, is the same setup. So if F is a finite free R complex, with non-trivial homology, then when I take the sum of the Lowy lengths of the homology, this is at least, and so this is how this theory of support varieties come in. It's actually the codimension of the support variety of R itself plus 1. And so by codimension, I just mean, N minus the dimension. And again, this has always been fixed throughout. It's the number of relations defining R. So N minus the dimension of the variety. Okay, and actually there's going to be a string of inequalities here. So this is at least the codimension of the K vector space span of this variety. So I'm viewing this in affine space, and then I have these vectors. I can take their span, so I potentially can get bigger, right? And then I take the codimension, so it's going to drop, right? Okay, or potentially. So let me pay attention to this one. And it turns out that this is at least the rank of row 2 of R. So I'll tell you what this is in a second, but what this is the radical, the homotopy Lie algebra. It's those radical elements in degree 2. And just to fit this in with what the ABIM theorem, this is at least the conormal rank of R plus 1. And one thing I want to really highlight is, in particular, if VR of R is not linear, not a linear space, then the inequality that was starred is actually a strict inequality. So it's a strictly stronger bound than the ABIM bound in those cases. And I think we saw an example earlier today where it's not a linear space. It was a union of 2 linear subspaces, right? So okay. So let me, yeah. Are there questions at all with the theorem? Okay. So yeah, so I guess I should at least explain what this row 2 is and how that plays a role in the picture. So, okay, so mark. Okay, so what is, I just want to tell you what row 2 is. So it's defined in terms of the homotopy Lie algebra. So pi star of R, so this is the homotopy Lie algebra. So I think it's been at least a couple years now since Ben Briggs told us about this gadget. Maybe it's appeared in a couple of other talks. But I just want to give you the quick definition, or just kind of give you an idea of what this thing is. Well, it's a graded Lie algebra. So in particular, it has some Lie bracket. And you can think of this roughly as a way to multiply elements, but it's a non-associative multiplication. And instead of associativity, it satisfies something called the Jacobi identity. And what rho 2 is it's the set of radical elements that live in degree 2. So it's the set of elements that live in pi 2, so degree 2 elements on top of the algebra, such that when I look at how this element brackets with the higher portion of pi, this is 0. For all I sufficiently large, for some I sufficiently large. Okay. Maybe it's worth saying, I mean, just as I guess a remark within a remark is, why this thing is interesting. So rho 2r has played an important role in the recent, I guess, solutions to, I guess, a conjecture of Vasconcelos. Vasconcelos's conjecture on the conormal module. That was due to Briggs, and I guess now published 2022, as well as a conjecture of Quillen on Andre Quillen, on vanishing of Andre Quillen homology modules. And this is due to Avramov in 99, but also recent work of Ben Briggs and Shrikant Iyengar. This also in 22. And so it's I don't know. I think it's an interesting thing that has been, or it's been interesting. It has been revived by these two very powerful applications that have appeared recently. I've been interested in myself. So actually, I think this theorem not only does it recover the Avramov, Pollitz, Iyengar, Miller result. Part of what's going on here that I think is quite interesting is it's somehow relating this this Lie algebra, the structure of this Lie algebra, to this geometric thing, this support variety of R. So there's something going on there as well. Okay, and so let's see, I only have a few minutes, so maybe I'll just give you a tiny bit of the idea of the kind of what goes into both theorem 1 and theorem 2, just a little bit of the idea. And then I want to end maybe with kind of a question and kind of further places to go. Okay, so just a slight idea. So maybe I'll just be vague here. So a main ingredient in both proofs, the proofs of theorem 1 and 2. So these are both with Ben and Olavisa, is the following. And this first step, I mean, this is kind of noticed or this was used by the ABIM paper. So if you look at the Lowy lengths of homology modules, actually, this is a more general thing. So if you take any complex, so anything in DFR at all, this is always at least what's called the level. I'm not going to define this, but I'll just kind of say what it does of M. So with respect to K. And so what this invariant is, it's some triangulated category invariant that happens in the derived category. And what it does is it measures, it basically counts the number of steps it takes to build M using K, starting from K. So if you think it's kind of a measure, it measures the number of mapping cones you need starting from K to build them up to the additive structure. Okay, so that's something that was exploited in the ABIM paper. And then what it turns out is you can show that this is at least the codimension of the cohomological support variety of M+1. And here, this makes use of some type of new intersection theorem, so a DG new intersection theorem. That was in the ABIM paper to begin with. But there's different techniques that go into establishing this inequality, but both proofs rely on this idea of basically passing to a derived category and then using the DG new intersection theorem in some way to establish this bound. Okay. Okay, so that maybe, unless there's questions, I might, especially because it's been a long talk, I might just end with a question, I think an interesting question. Are there questions on these two theorems? So, okay. All right, so one thing that theorem 2, I think makes it especially interesting is it opens up the door and attacking an old question of Avramov that I want to mention. So that's what I'll end with. So just to, so this is like a possible further direction. Okay. So just quickly, so we, just a matter of terminology, we say R admits an embedded deformation. If when we looked at this factorization, well, I guess maybe I'll just write it out. So if you can write R as R prime mod F, where F is non-zero divisor on R prime. So in other words, when you look at the factorization, sorry, completion always, okay. So the point is you want to be able to factor the original Cohen presentation where here you have a codimension 1 deformation. Okay. This is kind of a, a natural thing to ask is, can you figure out what, is there a way to detect whether your ring has an embedded deformation or not? So I think is a natural question. And question of Avramov in the late 80s. Suggested or maybe asked whether the Hammurabi-Lie algebra could detect this. So if there exists, or how about, just write it like this, does a central element in pi 2 of R, so determine an embedded deformation. So if you have a central element, and this just means, if your central, your bracket with everything is 0, does that determine an embedded deformation of R? And the converse is fine. So if you have an embedded deformation that determines a central element in pi 2, so it's asking the converse. And actually, according to this, so I don't know, what makes theorem 2, I think, especially interesting is that actually, if you can answer questions about the support variety, you get information about the radical, and the radical contains the central. So maybe I'll just end with this. So in light of theorem 2, it would suffice to answer the following question. If VR of R is contained in a hyperplane, does R admit an embedded deformation? So if you could answer this question because of the work in theorem 2, you'd actually be answering Lucio's question. And there's some reasons you might think of this. I mean, some of my earlier work has related embedded deformations to whether this variety is contained in a hyperplane, but it hasn't been fleshed out completely. But also, I don't know if I give this impression, but these varieties are very, you can calculate these things. So you can get your hands on these a little bit easier than sometimes the Hammurabi-Lie algebra. Because the Hammurabi-Lie algebra typically is some type of infinite object, whereas you can usually build these varieties with a finite amount of data. So it gives us maybe a new approach to attack an old and interesting problem about detecting embedded deformation. Maybe, yeah. So thanks everyone for listening. Stop here.
Thank you, Josh. Any questions?
When you say build VR of R with finite data, can you, I mean, will Macaulay 2 do it for you? And you plug it
Absolutely.
in?
So yeah, I mean, all you need, I mean, actually thanks to some of your code also. So you just need a system of higher homotopies. So you take a free resolution over of a regular ring, and you take a system of higher homotopies, and you can build these varieties. So it is a finite calculation. And there's actually some way I should mention. There's joint work with Eloisa Griffo and Yanina Letts, where we have a slightly different way to calculate it, and it's still, I mean, it doesn't use, it's a different calculation, but it still calculates it using Macaulay 2.
So this is already part of Macaulay 2 now?
No,
Being
we're
able to
working on it. So it's a thick subcategories package that we've been working on. and
Oh,
it should be,
okay.
In the Golid case, you said only two things can happen, the hypersurface or the whole thing for non-zero module.
Yeah.
Do you know when the hypersurface one happens?
Yeah, I mean, there's
In the Golid case?
Yeah, there's these so in representation theory, there's these L zeta modules. There's kind of this analog of these L zeta modules in this ring theoretic setting, and those are the ones that realize these hyperplanes. So they're actually just mapping cones of K with itself, like with a certain number of shifts. Like those are the ones that realize the hyperplanes. Good.
And the other question I had is that the example you did that was like x squared, xy, yz, and so on. That's Lucho's ring, or
Yeah, exactly.
Yeah,
So
is it
it's one
related to the thing that it's a counterexample for?
Is it related to the thing?
I
that's
mean,
account-
is your answer for the support variety being an interesting example, support variety wise, related to the fact that he has it as a counterexample for their existing MTG algebra structure? Is not related, right?
Oh, no, it is. I mean, well, in the sense that I think if you have a DG structure with like nice-ish properties, you're always going to get varieties that are linear spaces. So this thing is one that doesn't support. That's kind of why I started looking at this variety, or this ring in particular. It doesn't support this DG structure, and so it has a variety that's more interesting, kind of.
Have to go. Nice talk, however. Interesting subject.
Oh, thanks.
Yeah.
Okay. I guess we don't have